Okay, let me make some final remarks on this lesson and on the course up to now. So this lesson, the end of this lesson, completes the part of the course related to data abstraction. We've seen explicit state, object-oriented programming, Java, multiple inheritance exceptions. And from beginning until now, we have covered 3 of the 4 themes we're going to cover in this course. Functional programming, including recursion, invariant programming, and higher order programming. Also, language semantics. We've given a complete operational semantics, a completely formal abstract machine kernel language for all the language concepts we saw in this course, which lets you understand many things, including, for example, garbage collection and other things, execution time and so on, things that we have not gone into, but it gives a powerful base for further study and understanding of programming languages. The third theme is data abstraction. So we've given a broad and deep account of the different forms of data abstraction: objects, abstract data types, stateful, stateless, the role of state, and also how object-oriented programming builds on this. So let me now end the third theme on data abstraction, with a reflection on language design, and let me then introduce the final 4th theme. So we've discussed some of the principles that were used to design Java, which was designed in the early 1990s. For example, true data abstraction, encapsulation, where the internal representation of data cannot be accessed, allowing for garbage collection. Also, in Java, almost all entities are objects. Not all entities, it's not completely orthogonal. Also, the Java language has support for object-oriented design in the type system, for example, which is built for the substitution principle, and in polymorphism, for example. Now, the Scala language, developed in the early 2000s, has added 2 principles to this. First principle, it has a strict separation between mutable things, explicit state, and immutable things, constants, values that do not change. And this separation is such that both mutable and immutable are at the same level of importance in the language. They are not one more important than the other. And the second principle is that everything is an object, including functions. This principle was already used in Smalltalk before that, but Smalltalk is a completely stateful language. In Scala, this separation between mutable and immutable means that even functions which are immutable are objects, so they are in fact functional objects. And it's completely orthogonal. So if you look at these 2 principles, in addition to the principles coming from Java, these principles considerably increase Scala's expressive power compared to Java. And it doesn't seem like such a big difference, but in fact, it's an enormous difference when you start building things, how much more powerful the factorization that you can do in Scala. So we consider that Scala is truly a worthy successor to Java. Now, let me introduce now the final theme of the course, which is going to start in the next lesson. The final theme of the course will be concurrency. Concurrent entities are multiple activities that evolve independently and that may or may not talk to each other, collaborate to achieve common goal. There are 3 fundamental forms of concurrent programming, which I call deterministic data flow, message passing, and shared state. It's a very interesting fact that all 3 were invented in the early 1970s, along with many other concepts that are important. And I'm going to introduce these 3 concepts, these 3 approaches next lesson, but then we will concentrate on one of them, deterministic data flow. And we will present it in depth and we'll program in this model. So this model is extremely powerful, but still easy to use. And it deserves to be more widely known. It has, in some sense, been put in the shadow behind message passing and shared state, but undeservedly. And one, for example, very powerful principle that holds for deterministic data flow is that all the techniques of functional programming generalize to deterministic data flow. And in fact, functional programming patterns become concurrency patterns in deterministic data flow.